In the previous video, we talked about this idea that often, for many kinds of force, I can write the force as negative some derivative of some potential energy function as a function of distance in the direction where we care about the force. So this raises an interesting question of how can we tell if something is in equilibrium? Well, remember that the definition of equilibrium, translational equilibrium for an object, is that the net force on it be zero. So that's saying we're looking for places where the slope of this potential energy function is equal to zero. Now there are three kinds of equilibria that look like that. One is this type, where if I place an object exactly centered on top of that surface, I can see it'll stay there because the slope is zero. But if we perturb it even slightly, it's not going to come back. It's going to fall away and not return. So this is an equilibrium, but it's not stable. And that raises another interesting point about this metaphor of surface with slope as a way to understand force in a system, which is that to have stability, let's say first to have equilibrium, the condition is that we have force equal to zero, meaning the potential energy function has zero slope. But a condition for stability is that the second derivative of potential energy with respect to position has to be positive. And that'll give us a stable equilibrium. So here we have unstable. If we look at an equilibrium like this point right here, I can see if I push something away from that point, it's going to come right back, no matter what direction I push it. So if I have a concave up function, this one will be stable. This one is unstable. But in 3 dimensions, well, in 2 dimensions, we have other kinds of point. This point is like the middle of a Pringle chip or the center of a horse's back. And for that reason, this is called a saddle point. Here you can see that along this dimension, this function looks like a negative concave down parabola. And along this dimension, the function looks like a concave up parabola. So this saddle point has d squared u dx squared is less than 0, but d squared u dy squared is greater than 0. So this kind of point is stable in one direction, but unstable in the other direction, which ultimately makes it not stable. So in summary, we're looking for points to have equilibrium where the first derivative of the potential energy function as a function of space is equal to 0. And then for that equilibrium to be stable, we're looking for the second derivative to be greater than 0, meaning we're looking for a local minimum in potential energy.